Hello students, we have started halogen derivatives in which last time we have completed nucleophilic substitution reaction. Now we are going to start next point, nucleophilic substitution reaction mechanism. Now here S stands for substitution and N stands for nucleophilic, that is nucleophilic substitution reaction mechanism. Now we have seen various types of nucleophilic substitution reactions of alkyl halides, in which halogen atom from alkyl halide is substituted by or replaced by another atom or a group of atom like hydroxy group or cyanide group, nitro group or alkoxy group, etc. etc. In alkyl halides, the CX bond is a polar bond, that is, halogen atom in alkyl halide is more electronegative than that of carbon atom, and therefore the CX bond in alkyl halide is polar. And when the nucleophilic substitution reaction takes place, the CX bond from alkyl halide breaks heterolytically, that is, halogen atoms when breaks from carbon atom, it takes both bonded electron pair toward itself and form X- ion. Therefore carbon becomes electropositive. The halogen atom of alkyl halide is therefore called as leaving group. Leaving group is the group which leaves the carbon by taking away the bond pair of electrons. Now, in nucleophilic substitution reaction of alkyl halides, the substrate, that is alkyl halide, undergoes two changes during this nucleophilic substitution reaction. The original CX bond undergo heterolytic bond fission and new bond is formed between the carbon and the nucleophile using two electrons of the nucleophile. We know that nucleophile is an electron-rich species. These changes may occur in one or more steps. The description regarding the sequence and the way in which these two changes takes place in nucleophilic substitution reaction is called as mechanism of nucleophilic substitution reaction. There are two mechanisms which are observed in various nucleophilic substitution reaction. These are denoted as SN1 and SN2 mechanism. First we are going to see SN2 reaction mechanism, that is nucleophilic substitution bimolecular reaction. Here bimolecular stands for 2, that is N stands for nucleophilic, S stands for substitution and 2 stands for bimolecular. That is nucleophilic substitution bimolecular reaction. The best example of SN2 reaction mechanism is alkaline hydrolysis of methyl bromide. Now the reaction is, this is methyl bromide, that is CH3Br plus KOH, aqueous KOH. When this reaction mixture is heated, we'll get methyl alcohol, that is CH3OH plus potassium bromide, that is KBr. Now here Br is a leaving group and here OH is nucleophile. Kinetic expression for this reaction. This reaction is second order reaction, that is the rate of reaction depends upon the concentration of substrate, that is methyl bromide, and concentration of nucleophile, that is OH- ion. Therefore rate of reaction is directly proportional to the concentration of substrate, that is CH3Br, and concentration of nucleophile, that is OH- ion. Now we are going to see reaction mechanism of this SN2 reaction. Now this reaction takes place in one step, that is this is one step reaction with the simultaneous breaking of old bond and formation of new bond. Now this reaction mechanism is given below. Now look here, this is three-dimensional structure of CH3Br, that is methyl bromide. Now this Br is present from the front side of methyl bromide. Therefore, when this OH approach to this carbon atom from front side, this Br repels this OH minus ion due to steric hindrance also, and due to the same charge, that is Br have negative charge, or Br is also electron rich species and OH is also electron rich species. Therefore, there is repulsion between same charges. Therefore, Br repels OH minus ion from front side, and due to steric hindrance also, this OH cannot approach towards this carbon atom from front side. Therefore, backside attack of OH minus ion takes place. When these OH minus ions simultaneously comes towards carbon atom, the breaking of CBr bond starts simultaneously. That is, formation of COH bond starts and breaking of CBr bond starts simultaneously, and first transition state is observed. Now here, this in transition state, the carbon atom is bonded to 3 hydrogen atom, then 1 hydroxy group and 1 Br atom. Now this carbon atom is pentavalent, that is 5 atoms and groups are attached to this carbon atom. Therefore, it is pentavalent, and due to this pentavalent carbon atom, this transition state is unstable, short-lived state, which is fastly converted into product, that is methyl alcohol CH3OH plus Br minus ion. Now here, this OH is now from backside. In the substrate, Br or nucleophile or living group is present from the front side, but in the product, this OH is present from the backside of the carbon atom. Therefore, there is 100% inversion of configuration takes place. 100% inversion means if this compound is optically active compound, or this carbon atom is a asymmetric carbon atom, then if this is D isomer, then we'll get Leo isomer or L isomer. That is 100% of inversion of configuration occur during SN2 reaction mechanism. Look here, backside attack of nucleophile. From the front side, there is presence of halogen atom, which is nucleophile, which repels hydroxy group, that is OH minus ion, and thus attack of OH minus ion on carbon atom takes place from backside. This step is slow and rate determining step. This step is slow and rate determining step, that is, we can determine the rate of reaction by using this step. Now in slow step or in rate determining step, both nucleophile and methyl bromide take part, that is OH minus ion and CH3Br take part. Therefore, the rate of reaction is determined by using the concentration of both substrate and nucleophile. Now in the transition state, the nucleophile and leaving groups are bonded to carbon with partial bonds carry partial negative charge. That is, we have seen that there is partial negative charge on OH minus ion and partial negative charge on Br minus ion, and carbon is electropositive, that is, there is partial positive charge on carbon atom. The transition state contains pentacoordinate carbon, that is pentavalent carbon having 3 sigma bonds, in which one plane making bond angle of 120 degree with each other, and 2 partial covalent bonds along a line perpendicular to this plane. This transition state is fastly converted into product, that is methyl alcohol, in which 100% inversion of configuration takes place. Now we are going to see stereochemistry of SN2 reaction mechanism. When SN2 reaction mechanism is brought about at chiral carbon atom, that is asymmetric carbon atom, in an optically active substrate, the product is found to have opposite configuration compared to that of the substrate. That is, in other words, SN2 reaction is found to proceed with inversion of configuration, which we have seen. That is 100% inversion of configuration. This is like a flipping of an umbrella. Now, in case of rainy season, when there is stormy rain, then in air, when you come out with your umbrella, with the air, this umbrella becomes inverted. Like this, the structure of this methyl bromide, when it is converted into methanol, it is completely inverted, like inverted umbrella. It is known as Walden inversion. The inversion in configuration is the result of backside attack of nucleophile. This inversion of configuration occurs due to backside attack of nucleophile. Now we are going to see SN1 reaction mechanism. That is nucleophilic substitution unimolecular reaction. Example of this SN1 reaction mechanism is alkaline hydrolysis of tertiary butyl bromide, which gives tertiary butyl alcohol. The reaction is CH3 3 times CBr, that is tertiary butyl bromide. When it is boiled with aqueous potassium hydroxide, that is KOH, will get tertiary butyl alcohol, that is CH3 3 times COH plus potassium bromide, that is KBr. The kinetic expression for this reaction is first order reaction. That is, rate of reaction depends upon concentration of only one substrate, that is tertiary butyl bromide. Thus, this reaction is unimolecular reaction. Therefore, the rate of reaction is directly proportional to the concentration of tertiary butyl bromide. Now we are going to see the reaction mechanism of SN1 reaction. It is two-step reaction. Step first, formation of carbocation or carbonium ion. Carbocation or carbonium ion is nothing but positively charged carbon atom. The CBr bond undergo heterolysis. It is slow step to form trigonal planar carbocation. Ionization of tertiary butyl bromide takes place. Now look here, this the mechanism. It is a simple ionization reaction. This is slow rate determining step, and in rate determining step only tertiary butyl bromide take part. Therefore, rate of reaction is directly proportional to the concentration of tertiary butyl bromide. Now here, this is three-dimensional structure of tertiary butyl bromide. Now this CBr bond breaks heterolytically. This is slow and rate determining step, and this CBr bond breaks heterolytically, and so that this Br acquires all these bonded electron pair towards itself. Now look here, this Br have 6 electrons, and when Br minus ion forms, there are 8 electrons around this Br. Now Br minus ion forms, and along with this positively charged carbocation is formed, that is C+. This is tertiary butyl carbonium ion is formed, in which this carbon atom is positively charged. A carbocation intermediate is formed. The geometry of carbocation is trigonal planar, that is, the geometry of tertiary butyl carbonium ion is trigonal planar. This is simple ionization reaction in which CBr bond breaks heterolytically to form positively charged carbocation and negatively charged Br minus ion. Step second. Now attack of nucleophile. It is fast step in which attack of OH minus ion takes place from front side as well as from back side. Due to the front side attack, 50% retention of configuration, and due to the back side attack, 50% inversion of configuration takes place. Now look here the mechanism. This is carbocation, that is positively charged carbonium ion. Now here there is Me. Me is nothing but CH3 group. Me is a CH3 group, that is methyl group. Now this tertiary butyl carbocation is planar, trigonal planar. Geometry of this tertiary butyl carbonium ion is trigonal planar. Therefore OH minus ion attacks from front side also and from back side also. That is, here both front side attack and back side attack is equally possible, and therefore when front side attacks takes place, this is tertiary butyl alcohol in which there is 50% retention of configuration, that is substrate and this tertiary butyl alcohol have same configuration. But when backside attack of OH minus ion takes place, then we'll get 50% inversion of configuration. Due to backside attack, there is 50% inversion of configuration occur. Now stereochemistry. In second step, due to front side attack, 50% retention of configuration, and due to back side attack, 50% inversion of configuration takes place. If SN1 reaction is carried out at a symmetrical or chiral carbon atom in an optically active substance, the product formed is a racemic mixture. That is, here if we take, this is methyl group, this is ethyl group, and this is hydrogen atom, then this carbon atom becomes chiral or asymmetric carbon atom. Then when the substrate is dextrorotatory, then we'll get 50% dextro product and 50% Leo product in case of optically active compound. If SN1 reaction is carried out at a symmetrical or chiral carbon atom in an optically active substance, the product formed is a racemic mixture. That is, SN1 reaction proceeds mainly with racemization. That is, racemic mixture is formed. We know that the definition of racemic mixture is equimolecular mixture of dextro isomer and Leo isomer. Now during this SN1 reaction mechanism, if the optically active substance is used, then we'll get 50% dextro isomer of alcohol and 50% Leo isomer of alcohol. That is, racemic mixture is obtained. The reason of racemic mixture or racemization is due to formation of planar carbocation as intermediate. Now we are going to see factors influencing SN1 and SN2 mechanism. First factor is nature of substrate. Now first we are going to see SN2 reaction mechanism. In SN2 reaction mechanism, the transition state of SN2 mechanism is pentavalent and thus crowded. As a result, SN2 mechanism is favored in case of primary halides and least favored in tertiary halides. Now here pentavalent carbon atom is crowded, that is, this carbon atom is surrounded by 5 atoms or groups, and therefore there is crowding in the transition state, and therefore this SN2 mechanism is favored in primary halides and least favored in tertiary halides. Now second, SN1 reaction mechanism. During SN1 reaction mechanism, a planar carbocation intermediate is formed. It has no steric crowding. That is, this carbocation is surrounded by bulky alkyl groups, but these alkyl groups are only 3 alkyl groups. These bulky alkyl groups are electron donating groups, which stabilizes the positively charged carbocation, and thus bulky alkyl groups like methyl or ethyl groups can be easily accommodated in this planar carbocation. As a result, SN1 mechanism is most favored in tertiary halides and least favored in primary halides. That is, tertiary halides undergo nucleophilic substitution by SN1 mechanism, while primary halides undergo SN2 mechanism. Secondary halides react by either of the mechanism, that is by SN1 or SN2, or by mixed mechanism depending upon the exact conditions of the reaction. Second point, nucleophilicity of the reagent. Now we have seen that SN2 reaction mechanism is second order reaction and rate of reaction depends upon both concentration of methyl bromide, that is substrate, and concentration of nucleophile, that is OH minus ion. Therefore, a more powerful nucleophile attacks the substrate faster and favor SN2 mechanism. That is, SN2 mechanism is faster and favors by powerful nucleophile. The rate of SN1 reaction mechanism is independent of the nature of nucleophile. We have seen that the rate of reaction is directly proportional to the concentration of only substrate, that is tertiary butyl bromide. Therefore, the rate of SN1 reaction mechanism is independent of the nature of nucleophile. Nucleophile does not react in slow step of SN1 reaction. It waits till the carbocation intermediate is formed and then react fast with nucleophile. Therefore, SN1 reaction mechanism does not depend upon the rate of SN1 reaction mechanism does not depend upon the concentration of nucleophile. But in case of SN2 reaction mechanism, the powerful nucleophile attacks faster and favors the SN2 mechanism. Now third point, solvent polarity. In case of SN1 mechanism, we have seen that there is ionization of substrate takes place, that is tertiary butyl bromide undergo ionization to form tertiary butyl carbonium ion and halogen ion, that is Br minus ion, and thus SN1 mechanism proceed via formation of carbocation, that is ionization takes place, and therefore SN1 reaction proceed more rapidly in polar protic solvent than in case of aprotic solvent. That is, ionization of any compound occurs in case of polar solvent, and therefore SN1 reaction proceed more rapidly in polar protic solvent. In case of SN2 reaction mechanism, if we use the polar protic solvent, then this polar protic solvent decreases the rate of SN2 reaction mechanism. In the polar protic solvent, what happens? The nucleophile becomes stabilized and it does not react with the substrate and it decreases the rate of reaction, and thus in the rate determining step of SN2 mechanism, substrate as well as nucleophile is involved, and thus to activate the nucleophile to attack on the substrate, a protic or non-polar solvent or solvent of low polarity will favor SN2 mechanism. Now homework for you. Question first. Explain the SN2 reaction mechanism with example. Now answer of this question is in the slideshow. Question number 2. Explain the SN1 reaction mechanism with example. Same here. Answer is in the slideshow. Question number 3. Explain the factors affecting SN1 reaction mechanism. Answer of this question is also in the slideshow. Question number 4. Explain the factors affecting SN2 reaction mechanism. Question number 5. Give difference between SN1 and SN2 reaction mechanism. 6. Discuss the stereochemistry of SN1 reaction mechanism. And 7. Discuss the stereochemistry of SN2 reaction mechanism. Thank you.